The information and examples included in this summary presentation address the topics of construct validity and reliability of measurement procedures. Now, the objectives, the content and objectives for this particular part of the course and the presentations address part 4 of the class in general. So the first objective in this section involves you distinguishing between definitions and examples of measurement instruments and procedures, reliability estimates, and evidence of construct validity. So, in other words, what's the difference between reliability and validity? Well, validity is the degree to which measurement instruments and procedures actually measure the construct or other variables being measured. That's validity. So, for example, if you had an instrument that was designed to measure adolescent depression, and you were using this either as a counselor or as a researcher, you would want to know whether or not the instrument really was equal to the level of depression in the person who was using the instrument. So depression is a construct. The instrument is designed to measure the construct, and validity deals with how accurately does that measurement instrument measure the construct that you want it to measure. And again, this was addressed earlier in the course, but in this part of the notes, we're going to be looking at some of the ways that you can actually statistically measure, or at least estimate or collect evidence of validity. Now, reliability is different than validity. Reliability is the degree to which the measure of a construct is consistent or dependable. And you can collect evidence for the validity of an instrument used to define a construct, but you can estimate reliability. So reliability is synonymous with consistency. How consistently well does an instrument measure the construct that you want it to measure? So that's just a fundamental difference between validity and reliability. Given a description of reliability measures applied to a specific set of data, determine whether inter-rater, test-retest, split-half stability, or internal consistency reliability has been estimated. So let's take a look at these individually. So stability reliability is also called test-retest, and it's the degree to which a learner performance on the same assessment administered at 2 or more different times are similar. So in this case, you have an assessment and you administer it at a particular time, and then you administer it again at a different time, and hopefully it measures the same. Roughly, the performance on it will be similar among those who are taking it. So that's stability reliability. Split half reliability is kind of interesting. Split half reliability is a measure of the consistency between 2 halves of a construct being measured. For example, if you have a 6-item measure of a given construct, so let's say that the construct, all the items on a 6-item measure are designed to measure adolescent depression, like was addressed earlier. Okay, so after administering the items, or the instrument, the 6 items for the instrument to various members of your population, your sample, what you would do is you would randomly select 3 of the items, and then you would calculate the score or the performance for those 3 items, and then you would randomly select the 3 other items. They're different, and you calculate the scores for that, and then you correlate the 2, and you come up with a correlation that, again, you would do this for every participant who took the survey, and then you would take their scores, the one half of the scores and the other half, and you would correlate them and together as a group, and you should come up with a correlation coefficient. And 0.88 is a pretty good, it's a pretty high correlation. So that is an estimate of a high level of reliability for the items in that assessment instrument or that measurement instrument. So internal consistency reliability also deals with analyzing data once an instrument is administered. So let's go back to our example of a 6-item instrument that's designed to measure depression in adolescents. So what you would do to measure internal consistency is you simply measure how does performance on each item correlate with performance on all the other items, assuming that the 6 items are related to the same construct. So in this case, you could take item number 1 and correlate it with item 2, 3, 4, 5, and 6. So you take the scores, the performance scores from the people who responded to that instrument. And of course, if you notice on this, when you correlate item 1, performance on item 1 with performance on item 1, then that's a perfect correlation, 1.0. So that's why 1.0 is always going to be the score for this item being correlated with itself, obviously. So you do the same for item 2. You correlate it with all the other items that it hadn't been correlated with already. Do the same for 3, 4, 5, and 6. And what that does is statistically, then you could calculate the overall average correlation and get a correlation coefficient that again provides you with some evidence of validity. And a 0.91 is a good level of internal consistency. Now, what's really cool about doing this type of analysis is that it can help you identify individual items that might be problematic in your instrument. For example, you will notice you gave the same instrument and you ran the numbers through some good computer program that correlated the response to one item with responses to all the other items. And you'll notice that in this example, you have negative correlations with the with one of the items, negative correlation, and that resulted in an overall correlation that was much lower than the one previous. And what this would tell you, what this data would tell you, is that, oh wow, something is going on with item number 2. Either it was the wrong, the wording is off. I don't know. There's going to be some problem. If this was if this was an exam, for example, you could look at data like this and say, oh, well, item number 2, you probably have the wrong answer keyed in to the answer key, because what it shows you is a high negative correlation compared to how people performed on the other items. And so that is that would tell you that there's a real problem with item number 2. And by the way, after you take an exam in this class, I run all the numbers, all the correlation numbers for every item, and I examine them and I look for these red flags, because they will tell me that whether or not I have an item that's not functioning properly. And again, it could be that the wrong answer was keyed in, or the wording was such that that it applied to some other concept, something like that. So being able to interpret data like this is actually pretty important, because it's really important when you're designing assessment instruments to ensure that you have some evidence of reliability, or that you can estimate reliability in a good way. And finally, there's inter-rater reliability. And inter-rater reliability is sometimes called inter-observer reliability. And it's a measure of the consistency between 2 or more independent raters or observers of the same construct. So here we have a picture of two. They're different raters. They're making some observations by observing some video. They're in an observation room. Perhaps it's a counseling session. They're different raters. They look very similar, but obviously they're not because their hair is different color, and of course they're facing in a different direction. So they must be different raters. And this is an important thing to do if you are going to be collecting and analyzing data that involves scoring interactions that you actually observe, and perhaps have a a guide to help you record data off of that. But how good is that instrument? And if you have more than one rater, how consistent does one rater using the same instrument use it compared to the other? So inter-rater reliability is a really important value that needs to be estimated, and is almost always reported in scholarly work that does involve this type of data analysis. So here's another example. Suppose you were observing a science teacher who was interacting with students, and you were trying out a new assessment instrument, and you wanted to make sure that the person who was rating the teacher, that no matter who was rating the teacher using the instrument, that they would they would use the instrument consistently. Obviously, that's important if you're going to be using the same instrument for, by different raters and on different teachers. You'd want it to be consistent. So in this case, you have observer number one record their data, you have observer number two record their data, and then you correlate performances on those two rating observation sheets, and you hope that it's a high correlation. And again, the number that you end up with when you correlate any kind of reliability is a probability, that the probability that those two items are highly correlated, and it's called the R squared. And it's not really the probability. It is just the mathematical calculation of the correlation. And it is often reported in scholarly work. Here you see a data table that is reported by observers. This is, again, trying to correlate multiple observers using an instrument for math and physics classes. And you can see, based on, first of all, the data and the line, that this is a positive correlation, and it does have a high number, a high correlation number. Okay. Finally, the last objective in this related set is that you should be able to identify the purpose of the standard error of measurement. And you might be wondering, well, why would I have to do that? Well, really because it is something that is used in the literature, particularly education literature, when test scores or when surveys and the results of surveys are being reported. So the purpose of the standard error of measurement is that it's an estimate of the consistency of an individual's test performance on other equally difficult or easy tests. And again, it's based on mathematical calculations. But the only thing you really need to know about it is that, again, it estimates how consistent someone would be if they were to take a similar type of, or complete a similar type of instrument that was that was supposed to be equal. It's similar to the plus or minus percents of a polling statistic. Now, here is an example of how the standard error of measurement is reported. This is actually from a Virginia Standards of Learning assessment report that is sent to parents of children, of the child who takes an assessment. This one happens to be for 8th grade science. And you'll notice that it does report the SEM, the standard error of measurement. And what that tells you, it's 15, it's the plus or minus. And what that means is that if the student were to take this test again or take a similar test, they would likely score, if you look at the scale score, they earned a 403. That's a scale score. So they got a raw score of 30, and then it was assigned a value based on everybody else who took the exam. So what this tells you is that if they were to take this again, or an equally difficult test again, they would likely score between 388 and 418. So because the standard error measurement is 15, and that's the plus or minus, and they got a 403. So that would be the range. That would be what you would expect if they were to take this again. I mean, without any other preparation or anything like that. So that's the standard error of measurement. And again, it's included here because it relates to reliability. It is a reliability measure, but it's also used in the literature. For example, here is a table from a research paper where data were analyzed and the data were reported, and the standard error of measurement is included in the data. Notice also to the left of the standard error of measurement, a reliability estimate is also done, and that was probably again through some type of correlation procedure related to probably internal consistency. And that's it for this section of the material.